Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to talk on module Particle in Square Well Potential and Potential Barrier under the paper Quantum Mechanics. So students, let us see what we are going to learn in this module. We will learn to extend the procedure for solving the Schrodinger equation of a particle in square well potential for energies E greater than 0, that is, non-localized states, and study reflection coefficient. Also, we will solve the Schrodinger equation for a particle in a potential barrier to derive the expression for transmission probability. We will study quantum mechanical tunneling of the particle for square potential barrier. Also, we will learn the quantum mechanical behavior of a particle at potential barriers for energies exceeding the barrier potential height. In continuation of the preceding module, here we consider the particle having energies E greater than 0, that is, non-localized states in the square well potential. Using the continuity conditions on the wave functions in different regions, we study a typical quantum mechanical phenomena to estimate the non-zero probability of a particle incident on the potential well and getting reflected by it. The probability of reflection coefficient is found to be total at very low energies, that is E tending to 0, but then starts oscillating as E increase with a steadily decreasing upper bound, which does not depend on the width of the potential barrier. In the next part, we consider a barrier potential instead of a potential well and study the phenomena of quantum mechanical tunneling and obtain the expressions for transmission probability. Analogous to the case of quantum mechanical phenomena of reflection of particles by potential wells, we also get the expression for the reflection probability of particles having energy exceeding the barrier height. We begin with the non-localized states, that is, E greater than 0 in the square well, and discuss the quantum mechanical tunneling in square potential behavior. So, for the case when E is greater than 0, that is positive, and therefore twice me by h cut square, we now write 2m E by h cut square equals k square, and 2m into E plus v naught by h cut square equals beta square, where k and beta are greater than 0. Thus, the only change in the Schrodinger equation 15 represented in previous module will be able to replace minus alpha square by k square. The possible independent solutions in region 1 and 3 now are given by exponent iota kx and exponent minus iota kx instead of exponent alpha x and exponent minus alpha x. Here, the important difference is as x tends to infinity or x tends to minus infinity, both exponent iota kx and exponent minus iota kx remain finite, unlike the case considered earlier when one of the pair exponent alpha x and exponent minus alpha x become infinite as x tends to infinity or x tends to minus infinity. As a result, we have the general solutions as psi of x in region 1 is equal to c plus into exponent iota kx plus c minus into exponent minus iota kx, and psi of x in region 3 is equal to d plus into exponent iota kx plus d minus into exponent minus iota kx. where C plus, C minus, D plus, D minus are the unknown constants to be determined. In region 2, we have the same equation as the equation 18b in the previous module, for which we write the solution in the form psi of x in region 2 is equal to a plus into exponent iota beta x plus a minus into exponent minus iota beta x, so that it appears similar to equations 2a and 2b. Here, a plus is equal to a minus iota b by 2 and a minus is equal to a plus iota b by 2. A particle having the wave function defined by equation 2 is clearly not localized, in the sense it is not confined to any finite region of space, as is the case for a particle having negative energy. Physically, we have a picture where a particle of wave number k is incident from left to enter in region 1. A part of this is transmitted and another part is reflected back. Thus, in region 3, we can, without loss of generality and for simplifying the calculations, assume that there is only a transmitted wave. Consequently, the coefficient d minus can be taken to be 0. The ratio C minus by C plus gives the amplitude for reflection, while d plus by C plus gives the amplitude for tunneling to take place. Our main interest is to calculate the reflection coefficient for a quantum mechanical wave particle in the presence of the given square wave potential. Thus, to proceed further, the wave functions psi of x in region 1, psi of x in region 2 and psi of x in region 3 is to be defined in different regions and must be subjected to the boundary conditions defined by equation 22 and 24 at x is equal to minus a and x is equal to plus a respectively. However, unlike the case of bound states, the conditions do not lead to any restrictions on k or beta. Here, any energy E greater than 0 is an eigenvalue. The main reason is that for E greater than 0, we will have 5 unknown constants, and thus the continuity equations give only 4 linear homogeneous equations. Since the number of equations is less than the number of unknowns, an infinite number of solutions exist. In other words, the admissible solutions exist for every value of E greater than 0. Thus, the energy eigenvalues form a continuous, not a discrete set. Indeed, for complete determination of the eigenfunctions, we have to explicitly find the relations among coefficients appearing in equation 2, which we get from the continuity conditions. We first determine the ratio a minus divided by a plus and c plus divided by c minus by solving successively the equations 1 by psi in region 2 into d psi 2 by dx at x is equal to a is equal to 1 by psi in region 3 into d psi 3 by dx at x is equal to a, and 1 by psi in region 1 into d psi 1 by dx at x is equal to minus a is equal to 1 by psi 2 into d psi 2 by dx at x is equal to minus a, to get a plus into exponent iota beta a plus a minus into exponent minus iota beta a is equal to d plus into exponent I k a. The next equation is beta by k into, within the brackets, a plus into exponent iota beta a minus a minus into exponent minus iota beta a brackets close is equal to d plus exponent I k. On eliminating d plus from the above two equations, we have a plus divided by a minus is equal to exponent of minus 2 iota beta a into beta plus k divided by beta minus k. Now, from the second continuity equation given in equation 3, we have c minus by c plus into exponent 2 iota k is equal to k minus beta into exponent minus iota beta a into a plus divided by a minus plus k plus beta into exponent iota beta a divided by k plus beta into exponent minus iota beta a into a plus by a minus plus k minus beta into exponent iota beta a. We now substitute a plus by a minus from above equation, and after some manipulations we get the expression. Thus, square of modulus of c minus by c plus is equal to beta square minus k square whole square into sine square of 2 beta a divided by square of beta square minus k square into sine square 2 beta a plus 4 beta square k square. This is equal to the inverse of 1 plus 4 beta square k square divided by square of beta square minus k square into sine square 2 beta a. This is equal to the inverse of 1 plus 4 times e plus v naught into e divided by v naught square sine square within the brackets 2 times square root of e plus v naught divided by delta. In simplifying the last step in equation 7, we have used the relations beta square minus k square equals 2m v naught by h cut square, and k square is equal to 2me by h cut square, and delta is equal to h cut square by 2ma square. Thus, equation 7 gives the probability of reflection of a particle in a square well potential, which is defined in the preceding module. Clearly, for very low energies, E tending to 0, the reflection is almost total. As E by V naught increases, reflection probability starts oscillating between 0 and a steadily decreasing upper bound, which is defined by the function inverse of 1 plus 4e into E plus V naught divided by V naught square. This bound depends only on E by V naught and not on the width of potential well, but the frequency of the oscillatory changes in reflection probability depend on it through the parameter delta. This behavior is graphically depicted in the following figure. Let us now proceed to consider a potential barrier instead of a potential well. This problem is of special significance since it illustrates how the wave function penetrates into classical forbidden region, that is, the ability of particles to tunnel through the barrier V naught exceeding their energy E. In figure 2, they is shown a square potential barrier of height V naught and width 2a. Vx is defined as Vx is equal to 0 for values of x less than minus a, that is in region 1. Vx is defined to be V naught for values of x lying between minus a to a, which is defined as region 2, and Vx is equal to 0 for x greater than a, that is in region 3. We now discuss the solution of Schrodinger equation for square well potential. We start once again by writing the solutions of the Schrodinger equation given as minus h cut square by 2m into d2 psi by dx square plus 2m by h cut square into E minus V into psi is equal to 0 into the three regions, defining k square is equal to 2me by h cut square and gamma square is equal to 2m into v naught minus c by h cut square. For e greater than 0 and less than v naught, we have psi of x in region 1 is equal to c plus into exponent iota kx plus c minus into exponent minus iota kx, where x is less than minus a. For the region 2, where x lies between minus a to a, we have psi of x is equal to a plus into exponent gamma x plus a minus into exponent minus gamma x. For the region 3, where x is greater than a, we have psi of x is equal to d plus into exponent ikx plus g minus into exponent minus iota kx. We now discuss the particles reflected from the barrier. Note that this wave function is different from the earlier one only in having the real constant gamma in the exponent instead of iota times beta in region 2. Considering the particles incident on the barrier only from the left side, the particles having positive momentum by the part c plus exponent iota kx of psi 1. The other part c minus into exponent minus iota kx of psi 1 represents particles moving with momentum minus h cut k away from the barrier. It therefore describes particles reflected from the barrier. In region 2, there are no particles moving to the left which are approaching the barrier. Thus, we have d minus is equal to 0 and the wave function in region 3 reduces to d plus into exponential iota kx, which represents particles moving to the right, which could come only tunneling through the barrier from region on 1. The ratio d plus by c plus gives the amplitude for the tunneling to take place, and c minus by c plus is the amplitude for reflection. The corresponding probabilities, the square of modulus g plus by c plus and square of modulus c minus by c plus are determined by employing the same procedure used earlier. That is, by applying the continuity conditions at x is equal to minus a and x is equal to plus a to the wave function defined by equation 12, subject to the condition d minus is equal to 0. Thus we get a minus by a plus is equal to gamma minus iota k by gamma plus iota k into exponent of 2 gamma a, and c minus by c plus is equal to minus iota into k square plus gamma square into exponent minus 2 iota k into sine hyperbolic of 2 gamma a. The entire terms are divided by minus iota into k square minus gamma square into sine hyperbolic of 2 gamma a plus 2 gamma k into cos hyperbolic of 2 gamma a. We then express the ratios d plus by a plus and a plus by c plus in terms of the expressions given above by solving psi in region 2 is equal to psi in region 3 at x is equal to a and psi in region 1 is equal to psi in region 3 at x is equal to minus a. We thus get the transmission amplitude as d plus divided by c plus is equal to 2 times gamma k into exponent minus 2 iota k divided by minus iota into k square minus gamma square into sine hyperbolic 2 gamma a plus 2 gamma k into cos hyperbolic 2 gamma a. The probability for tunneling, that is the transition probability, is then given by T is equal to the square of modulus D plus by C plus, which is equal to the inverse of 1 plus square of k square plus gamma square divided by 4 gamma square k square into sine hyperbolic square 2 gamma a. It can be easily verified from equation 14 that the reflection coefficient is just IT. The expression given by equation 16 can be reduced further by expressing it in terms of energies involved by using the relations square of gamma A is equal to V naught minus E divided by delta, and square of Ka is equal to E divided by delta to write T is equal to square of modulus D plus by C plus, which is equal to the inverse of 1 plus V naught square divided by 4 times V naught minus E into sine hyperbolic square within the brackets twice of square root of V naught minus E by delta. Notice that sine hyperbolic y is equal to 1 by 2 exponent of y minus exponent of minus y, which is a rapidly increasing function of y and can be approximated as e raised to power y by 2 for y much greater than 1. Therefore, except when twice of square root of V naught minus E by delta is less than equal to 1, the second term within the square bracket in equation 17 dominates. Using this approximation, we write T is equal to 16 times V naught minus E into E by V naught square into exponent minus 4 into square root of V naught minus E by delta. Thus, we have obtained the expression for transmission probability. The figure shows the plot of transmission probability as a function of E by V naught for various values of V naught by delta. We now discuss the behavior of tunneling probability. We can see from the figure that as soon as the energy difference V naught minus E exceeds the energy delta, the tunneling probability starts falling off exponentially. On the other hand, if the particle energy is very close to the top of potential barrier, then V naught minus E by delta is less than equal to 1. Then the approximation sine hyperbolic y is appropriate and equation 17 reduces to T is equal to inverse of 1 plus V naught square by 4 times V naught minus E into 4 times V naught minus E by delta. This is equal to inverse of 1 plus V naught square by E into delta. We next discuss the reflection at potential barriers and wells. The probability of reflection coefficient can be obtained by simply modifying equation 14, where for the case E greater than V naught, we now write 2m into V naught minus E divided by h cut square is equal to minus gamma prime square instead of gamma square. As a result, we replace gamma by iota gamma prime in equation 14 for reflection amplitude, and we get C minus by C plus is equal to k square minus gamma prime square into exponent minus 2 iota k into sine 2 gamma prime a divided by k square plus gamma prime square into sine 2 gamma prime a plus 2 times iota gamma prime k into cos 2 gamma prime a. The reflection probability is therefore given by the square of modulus of ratio of C minus and to C plus is equal to the inverse of 1 plus 4k square into gamma prime square divided by square of k square minus gamma prime square into sine square 2 gamma prime a. Substituting the value of gamma prime square from equation 20 and k square equals 2me by h cut square and writing delta is equal to h cut square by 2ma square, we finally write inverse of 1 plus 4e into e minus v naught divided by v naught square into sine square twice of square root of e minus v naught by delta. Now we move on to the comparison of the expressions for reflection coefficient. It would be interesting to compare the expression for the reflection coefficient described by equation 7 obtained for the non-localized states of a potential will. Note that the wave function described by equation 2 of that case differs from equation 12 only in having iota times beta in place of gamma, or equivalently I can say beta in place of gamma prime. With this replacement, equation 22 and the corresponding replacement of E minus V naught by E plus V naught in equation 23, we recover the formula given by equation 7 for the probability of reflection by a potential will. So students, let us now summarize what we have learned in this module. In this module, we studied to learn and extend the procedure for solving the Schrodinger equation of a particle in square well potential for energies E greater than 0, that is non-localized state, and also to study the reflection coefficient. We solved the Schrodinger equation for a particle in a potential barrier to derive the expression for transmission probability. We came to know quantum mechanical tunneling of the particle for square potential barrier. We learned the quantum mechanical behavior of a particle at potential barriers for energies exceeding the barrier potential height. Thank you students for your kind attention.